Hola, Madrid. Thanks everyone for attending our presentation. It's a big pleasure for us to be here. My name is Adam and I run a company called Getting Data. That is a software house that builds complex big data solutions for other companies. Before that, I had been working with big data technologies for 5 years, mostly at Spotify, Truecaller, and a few other companies. And today, I'm not alone. There is also my colleague.
Yeah, I'm Dawid Wysakowicz, and I work with Adam at Getting Data, implementing streaming solutions, and I'm also Apache Flink committer.
Yes, and together we'll explain you why and when stream processing can be better than classic batch. And I will start with my personal story. When I worked at Spotify and a few other places, I had implemented many big data pipelines, and I was really proud of them. In my opinion, they were very, very cool, because each time I implemented them, I used best available technologies and techniques. But each half a year later, I was really surprised to discover that my big data pipelines were not that cool as they supposed to be. And today, I actually think that they were too complex. They had too many moving parts. They also ran too slowly, and what even worse, they generated incorrect results, even there were no bugs in my code. I will explain what I exactly mean by example, and this example will be about analyzing user sessions. It will be inspired by Spotify, because this is the company when I spent some time working at. But of course, it can be applied to many other companies from sectors like e-commerce, media, IoT. When you analyze user sessions at Spotify, you can compute basic statistics like the duration of the session, number of songs, also more complex things like the current mood of the user. And you can do at least 3 different things with the output of your session analytics jobs. First of all, you can visualize it. For instance, you can create dashboards that show how long users are listening to Discover Weekly playlist, how many consecutive songs they listen to, how many songs they skip, and so on. If you don't know, Discover Weekly is personalized playlist created for each user by Spotify each week, and it contains fresh, new music that a user might like. And because this playlist is generated each week for each user, those statistics might change depending on how good music recommendations are. So it makes definitely sense to visualize those numbers and look at them. It also makes sense to send internal notification or maybe alert when those metrics changes dramatically. For instance, if we notice that Australian users are listening to Discover Weekly not as long as they usually do, then we can send internal notification so that someone can investigate that case and maybe solve potential problem before European or American users wake up. Last but not least, we can use the insights from the current user session to recommend better songs or ads based on what user is currently doing, what songs the user is listening to, or maybe what user is doing, like working, exercising, relaxing. And I will tell you how popular big data technologies might solve those problems, and I will start with classic batch approach. Many companies use Kafka, Spark, Hadoop, Uzi for building big data pipelines. And in this case, the user events that represent user activity will be sent continuously to Kafka in real time. But then we can have a tool like Kami or Goblin that will be periodically copying data from Kafka to HDFS, let's say each hour. And once we have our data in HDFS, we can have Spark jobs that will combine individual user events into complete user sessions. And those Spark jobs can be scheduled periodically, each hour, maybe each day, by a tool like Uzi or Airflow. And in the logic of your Spark job, you might do a few different things. First of all, you need to group events by user ID. Within each group, you need to sort them by timestamp, remove duplicates, and what's the most important, you need to assign the same session ID to user events that occur close to each other. And this would be the most tricky because at Spotify, it's possible that a single user session might take many hours. For example, when a user is listening music at office in work. So we don't know the duration of the session up front. So if you schedule your Spark job each hour, then you have to process not only data from this particular hour, but also from the previous hour to make sure that you from the previous hours to make sure that you create complete user session with all events from the same session that are located in different hourly partitions. Also, the alternative is that you schedule your Spark job daily, so you have a chance to create as many complete user sessions as possible, but then you will run into problems with the sessions that started before midnight and ended after the midnight. And if you are interested in details, something stopped working, I think. The pointer might not work, I think.
Yeah, we'll try maybe one more time. Pointing there.
Okay, if you are interested in more details, there is actually a book that explains all those sessionization steps on clickstream example. And even though there is a book that explains how to do that, and many companies have deployed that in production, it has a number of disadvantages. First of all, it has a number of too many moving parts. So you need to learn tools like Kami for ingestion, Uzi for scheduling. You need to decide how to partition data in HDFS. And you need to integrate many different components into a single pipeline and make sure that all those components are up and running. And based on our experience, something will fail from time to time because you will run into the issue with your gluing code or the tools that you use. However, even if your pipeline finished successfully, you will wait hours to see the results because we use classic batch processing technologies. And if you see the output after hours, obviously the value of your data will be lower, and you could use this data only for making historical or reactive decision. However, if you would like to make actionable or predictive decisions like triggering instant alert or detecting some frauds or updating music recommendations based on what user is actually doing and feeling right now, then you need to generate your numbers with much lower latency. And for this reason, we can use a technology like Spark Streaming, which is micro-batch technology. So with Spark Streaming, the infrastructure is much simpler because you don't need Kami, because Spark Streaming job can consume data directly from Kafka. You don't need tool like Uzi for scheduling because Spark Streaming job will continuously run 24 hours per day. And also, you will get results faster because you can configure Spark Streaming job to process your data in smaller batches created each 15 minutes. So those are the advantages, but there are also disadvantages. And the problem with Spark Streaming is the fact that sessionization is not natively supported. And to achieve it, you need to implement own custom code. This is needed because internally, Spark Streaming is dividing the stream of new events into separate batches created let's say each 15 minutes. And it might happen that a single user session might have user events that are located in many of those micro batches. So you need to implement own code that is able to create a single user session out of events that are stored in different batches when those batches are processed independently. And this is possible with the map with state function that keeps internal user state across the batches. And there are few blog posts that describe how to do that, and you can refer them to see the code, to see the details that should be done. However, those blog posts doesn't mention other difficult problems that might happen to your data. They only focus how to build a user session. And one of the serious problems that might happen to your data is when data arrives too late. With Spotify, it's possible to download music to your device and listen it in offline mode. So imagine that you take a flight to Madrid and you listen to Spotify in your mobile phone, and those events will not be sent to Kafka because you don't have internet connection. So they will be buffered locally on your device. But later, when you connect the internet, all those previously buffered events will be sent to Kafka immediately because now we have internet connection. And those events will pretend to look as new events. And if you don't have the application code that is able to differentiate the original event time that says when the events were originally generated, then you might process all this data, old and new data together in the same microbatch. So you might generate the dashboard that shows that we have many songs listened to at this hour, but not songs at all 2 hours ago. And the variation of that problem can happen when we switch device. So imagine that we take a flight to Madrid again, but this time we listen songs in the offline mode on our desktop. So of course, those events are not sent to Kafka because we don't have internet connection. But your flight ends, you shut down your laptop, you try to get out of the airport, and you take a taxi. And in a taxi, you listen to Spotify on your mobile phone. And those mobile events are sent to Kafka immediately because we have internet connection. And later you arrive home, you relax on your sofa. You relax on your sofa and you turn on your laptop again. So those laptop events are sent to Kafka immediately. So as we see, for a single user, we have data that are sent out of order. First from mobile, then from desktop, but we know that the reality is different. So if your application code doesn't handle this situation, we'll get incorrect results because we'll process data in wrong order. As you see, there is a number of issues that we need to tackle. Some of them are caused by batch or micro-batch technologies that force us to think about our data not as a stream of events, but as a separate batches, files in HDFS or micro-batches, and you have problems on the border of those batches. And also some problems can be caused when our data comes late or out of order, and we need to have some application logic to process this data correctly. And now I will ask Dawid to explain you how modern stream processing engines can be used to solve those problems.
Yes, exactly. So as Adam just said, no matter what batch technology we decide to use, we still need to face all those problems with time-specific problems, etc. But let's ask ourselves a question. Do we really want to, wouldn't it be easier if we approach those problems with a different mindset? Do we really want to process our data with some micro-batch or batch abstraction rather than as a stream as they truly arrive? Or is it just because we always found stream processing hard to implement, or we didn't have the right tools to do so? So we believe that with modern stream processing engines, we can do it very easily, and what's most important, correctly. So one of those modern stream processing engines is Apache Flink. And just as with the Spark streaming approach, the Spark streaming solution, we can read the data directly from Kafka. So we are out of the problem of many moving parts. But in that solution, we treat our stream as a stream, not as as such some micro batches. Yeah, but of course, it doesn't mean that the further processing will be any harder. In fact, it's quite the opposite. So I will try to show you just in a second. So let's imagine that we want to count how many songs a user listened in a single user session that is constituted by some gap between two events, some maximal gap between two events that should end up in the same session. So the first thing we should do is to read the data from Kafka. Flink comes with implementation of Kafka consumer that, with the internal mechanism of checkpointing, provides us with the so desired exactly once semantic. Later on, we should group the events by some user ID because we want to analyze user sessions. And later on, we just say that we want to group our events in some session windows. All we have to do in here is just to provide the threshold for the gap that constitutes the window. And to finish the very basic example, we just need to apply our aggregate function. And for example, all the problems with cross-batch border events and out-of-order events are already resolved. But we don't end up here because we still have some room for improvement. For example, we want to handle some late data. So for example, we can say that we expect that the data can be late, for example, for an hour or so, and Flink will keep the internal state of all the sessions for that extra amount of time, so that when some late arrivals comes, we can update that state and, for example, push down to some independent downstream jobs or some sync. Yeah. Another thing that we can do is we may want to shorten the feedback loop. So, for example, we don't get the results only on the end of the session, but let's say we want to have insight in our data every, let's say, 10 minutes. So we can provide Flink with some custom implementation of trigger that will generate the intermediate data every now and then. Yeah, I think that this of course, it's not like a full code because we wouldn't. Yeah, it's hard to present a whole code in a conference. But if you are interested, you can check out a working solution in our GitHub. Yeah, what's not? I think that this few lines of code shows very well that all the time-specific issues are easily resolvable with Apache Flink, but maybe what's not visible from the code is that Apache Flink is still a very efficient processing engine that comes with a very low latency and high throughput, and also has a very unique mechanism of checkpointing that allows us to provide real exactly one stateful processing. And all those things are confirmed by the last year user survey that you can check out the results in those links, or wait probably a month or two for this year edition of the user survey. Yeah. Okay. We know that there is no time for Q&A, but as we love questions so much, then that's why we prepared some questions ourselves. And the first question we have is, how can I reprocess data? With batch solutions, it's pretty straightforward. We would probably run the same job over, maybe not the same, but some job over the same set of files. and we're done. With Apache Flink, it's pretty much similar, thanks to the save point mechanism that allows us to take, let's say, snapshot of all the internal state of the processing. So we can later on rewind to a particular moment in time that when the save point was taken, and the job can be reprocessed from some point, for example, in our Kafka stream. What's very important in here is that the save point is not tightly coupled to the exact version of the code that it was generated with. So we can use that mechanism also for some bug fixing, so that we can fix some bug and reply the processing on the same data. Or, for example, we can use that mechanism for upgrading Apache Flink. So it's really powerful feature. Another question that may arise is, what if the data is no longer available in Kafka, maybe because of some retention policy or something like that? So we can reprocess, we can store the historical data, for example, in HDFS or any other distributed file system, and we can use Apache Flink with the same processing pipeline consuming data from HDFS. The only difference is that we should consider, we should be able to reply the order of the events, or at least be able to provide some rules on the timestamp in the event. So, for example, we should store in those files events from the same period of time. Yeah, but it's doable. Another thing, so that's maybe it for the very technical part. And another question that may arise, so what are the usual applications of stream processing? So we believe that there are two main groups of such use cases that we should use stream processing engines. So the first one is stream analytics. So imagine a case when Spotify went live in South America in a dozen of countries at the same time. And of course, on dozens of different clients. It was vital to have the insight into the data, what's going on with the going live as soon as possible, so that they could react quickly to some bug fixing, to some problems, so that users wouldn't be disappointed by the platform. So it's vital in that case, it's vital for the admins, the DevOps, to have the insight as soon as possible to be able to react. So it's the first group of applications, and the other one is use cases when we need to provide the data to the end user as soon as possible, or maybe not as soon as possible, but continuously, 24 hours per day, 7 days per week. So in Spotify, the use case is, for example, the friend activity feed. So that it is a feature that shows us what our friends are currently using to. So the first version, without any streaming processing logic, was that each event was presented to the end user, but it ended up that, for example, plays of the same song by the same friend of us ended up polluting whole the area. So later on, there should it was needed to introduce at least the duplicating logic, and it perfectly fits for streaming processing. But so, another question is, so the streaming has so many advantages. So should we forget about batch at all, or maybe batch is good for some other cases? And we believe that there still are some cases that batch is a perfect fit. For example, when we need to do some ad hoc analysis, so with some notebooks to find out some some rules about our data, but our bounded data, then batch solutions are the best to go. And another very important one is that if we have some major high-level libraries, for example, machine learning libraries, and we want to train some models on bounded data, then probably also batch solutions would be a better fit. Yeah.
To conclude, we would like to tell you a quick summary. So based on our observation and also community observation, it happens that in most our business cases, the data comes as a stream. Think about clickstream, logs, metrics generated by your events. So it does make sense to process the stream of data using stream processing technologies. It doesn't make sense to make our job harder by dividing it into batches or micro batches and run into problems at the border of those batches. Also, stream processing is not only about generating the alerts or getting results as fast as possible. It's also about accuracy, especially when we have data that arrives late or out of order. It also makes our infrastructure simpler because we have fewer moving parts, and also our code is nicer because we have the support for handling event time. We can have session windows, early triggers, and so on. So this means that modern stream processing engines can be used for many typical use cases like ETL pipelines, computing KPI metrics, or generating numbers for our reports. So those use cases are the use cases where many companies have been using batch processing technologies traditionally, but if you switch to stream processing technologies, you will avoid many serious problems and you will get correct output. So this is what we highly recommend you. And if you expect us to give you one takeaway message, how to decide which approach to follow, whether you should do batch processing or stream processing approach, think about how the data arrives to your system. So if your data arrives continuously all the time, and then probably it means that you have streaming problem. And streaming problem is better to solve using dedicated stream processing technologies, not batch jobs. And here we'll end our presentation. Thank you for attending, and we'll be also here today and tomorrow. So if you have any other question after this presentation, we'll be happy to answer them. Thanks.
Thanks a lot.